This is the screencast for section 7.3, example 5, finding volumes using cylindrical shells. Again, the region bounded by the curves y equals 4 minus x squared and y equals x, these, and x equals 0, so the y-axis, is revolved about the y-axis to form a solid. Use cylindrical shells to find the volume of the solid. So this time, we are going to be taking our area, making edges of shells vertically within it, and then revolving that around the y-axis, which will create these vertical shells. So to see what's going to happen, I drew an edge of a shell connecting the two curves. I'll draw the opposite edge on the opposite side of the y-axis because that's what it's getting rotated around, and draw the top and bottom because of the rotation. Those would be circles, so I can kind of see what a shell would look like. Alright, so we know that the cross section is going to be a cylindrical shell. It's going to look like this. Its area is then 2 pi rh, so we got to figure out what the radius is. Well, the radius is just going to be x. The radius is a distance from the y-axis to the x-coordinate, to the curve, so it's just the x-coordinate. Then, the height is going to be the distance between those two curves. And yeah, it's going to be bigger towards the y-axis and smaller away from the y-axis, but it's still the distance between the two curves. So 4 minus x squared minus x. So this top distance, so all the way up from the x-axis to the top curve, minus the distance to the little curve, will leave us just with the distance in between. So that's the height. So now means the area is going to be 2 pi r, which is x, times the height, which is 4 minus x squared minus x. And I'll distribute that so that my integral is a little easier to work with. So now the volume is going to be the antiderivative from 0, so the edges of the cans, like let's say the right edge of the can is going to be stacked starting at 0, and then it's going to go out to this intersection. So I got to figure out what that intersection is. So I'm going to set the 4 minus x squared equal to x, set it equal to 0, use quadratic formula, and I get negative 1 plus the square root of 17 over 2. Negative 1 minus the square root of 17 over 2 would be the intersection on the left side, like where the parabola comes down and then meets y equals x. So remember, this is a parabola. It's going to come all the way down here and then meet y equals x. We're not worried about the negative intersection. We want the positive one over here. So that means the volume is going to stretch from, or the antiderivative is going to go from 0 to negative 1 plus the square root of 17 all over 2. Now, the surface area of each of these cylindrical shells is 2 pi, which I stuck on the outside, times negative x cubed minus x squared plus 4x. Give each shell a little bit of thickness with a dx. This is a little change in the x-axis. That's why we're using x's here. Yes, it's revolving around the y-axis, but the thickness of the shell, the thickness of the can, is going to be a little change on the x-axis. So it's a dx problem. And we'll integrate, and we get 13.327 cubic units. The now try problem number 35 says use the cylindrical shell method to find the volume of the solid generated by revolving the region bounded by the curves about the y-axis. So here's my two curves, y equals x and y equals negative x over 2, which I graphed on my calculator. This looks very hard to see what is exactly going on in this revolution. Okay, so let's think about, first of all, it's being revolved around the y-axis, so I draw my little circle to show that. Then it's the curve bounded by y equals x, y equals negative x over 2, and x equals 2. So I'm looking at this triangular shape because that has all three boundaries. So this is it. This is all I'm working with. This triangular piece. Now, I know it looks weird because this is almost symmetrical, so it's almost like you should be using that other side, but you have to ignore that. You're only working with that triangular portion. Do not worry about what's on the other side of this graph. We're only working with the triangular portion of this curve. That's the part that's going to get revolved. So I'm going to draw an edge of one of my shells connecting y equals x and y equals negative x plus 2. My shells are being revolved around the y-axis, so they are vertical shells. I'm going to draw the opposite edge across the y-axis and then show the revolution by creating the circular top and bottom. And now we have a picture of what the shell is going to look like. So our cross section are cylindrical shells. They're going to have the area 2 pi rh. So now we just need to figure out what the radius is and what the height is. Well, the radius, if you can see here, is going to be from the y-axis out to the curve. So that is a horizontal distance that's just going to be my x-coordinate. The height is the connection between the top and bottom curve. Well, that height is just the top curve minus the bottom curve. So x, and then really the distance between the x-axis and negative x plus 2 would be negative, but if we're subtracting it, it would be adding that distance to the top distance, creating the full height of the cylinder. So now the area is 2 pi times x plus x over 2. I'll simplify that so my integral is a little bit easier to work with. Now my volume is going to be created by stacking these cans. One edge, the right edge of the can, is going to go from 0 all the way out to 2 on the x-axis. The area of the cylindrical shell is 3 pi x squared. Give each of those shells a little thickness. Integrate, fundamental theorem part 2, and we get 8 pi units cubed.